Log on, tune in, find out. Another good idea from Cambridge.
Thank the organizers for inviting me to speak here. It's always very good to be back. So I wanted to talk about some recent developments in Lagrangian duality concerning the connection between topological amplitudes and knot invariant. So the title would be Lagrangian cycles and knots at large n. And this is with Vivek Shende and Kumrum Vafa, paper about 2 months ago or less. And there is some also to appear soon with Zheng Hua and Jan Swebelman. Also, we had many discussions that have helped shaping up this project with Alexei Oblomkov. All right, so this is going to be a pretty much a physics talk. So I'm not gonna insist on the technical details, and I'm gonna try to suppress as much as possible, sort of mathematical aspects. So I want to start by recalling Lagrangian duality. A brief account of Lagrangian duality for topological strings. So this is work done more than 10 years ago. More specifically, I'm interested in the first example of Lagrangian duality for topological strings, which was discovered by Gopal Kumar and Vafa, which was this Lagrangian duality for the conifold. So this was, if I'm not mistaken, this was in 99, I believe. I'm going to refer to this as GV. And then the example, example of Ogurian Vafa, who was the first. It was the first example adding knots to the picture. So also around 99 or 2000. This is, I'm going to talk about this OV. This is you add Lagrangian duality for the unknot. So as I said, this is. And it's one of the situations in which pretty much since then, pretty much it was hard to make progress because to sort of upgrade to generalize these results for more complicated knots for reasons I'm going to explain. And then suddenly there is a new kind of motivation, and there was new motivation to go back to this problem, which was due to some conjectures of Oblomkov and Shende. So okay, so let me see. So let me remind everybody knows that there is a conifold transition. Just to fix notation here, which goes from something smooth. I'm going to call X mu, which is a hypersurface of the form xz plus yw equals mu, to a singular threefold, which is xz plus yw equals 0, and this has a resolution, a small resolution, Calabi-Yau resolution, which is isomorphic to the total space of the of 2 copies of O minus 1 over P1. And in this setup, what is being done in the Lagrangian duality is that you have two sides. Of course, it's a duality, so you're going to have two sides. So this side, so first of all, it's not like mirror symmetry that exchanges A and B models. We are working only with A models throughout. But here, this side is what I'm going to refer to as a deformation side. And let me mention that all these manifolds are actually asymplectic manifolds, are isomorphic to T star LF3 asymplectic manifolds. But obviously, you have different complex structures labeled by mu. So there is a deformation side in which you're supposed to compute to put n Lagrangian branes on the 0 section. So 0 section over S3, obviously. So you have a 3-sphere, which happens to be actually a special Lagrangian. You put anti-branes there, and you're supposed to compute a topological A model with boundary there. And this one is by work of Witten, which is back in 1991, is equivalent to doing Wheeler and Chern-Simons theory on S3. And if you want to exhibit this as an open string expansion, you're supposed to take a Lagrangian limit. Take the 't Hooft Lagrangian limit in order to actually exhibit this partition function as a topological string expansion. And in particular, I'm going to say a bit later in just in a few minutes, what the string coupling constant is. Okay. Yeah. All right. So that's one side. So now, basically what we are told is to take the Chern-Simons partition function and expand it in the Lagrangian limit. And the other side here is to look at, this is, I'm going to call this on the resolution side or the blow-up side. So we're doing again a model, so we want to compute a topological A model on Y. There is no branes this time. So we just look at a topological A model on Y, and the conjecture on what was observed by Gopal Kumar and Vafa, in fact, that these things are equal. So the relation they wrote down, they proved, was that if you take, well, the analytic part of the Chern-Simons theory, so there is some non-analytic part that I'm not going to discuss. So we have a level k and the integer n, and you take this Lagrangian limit in the 't Hooft sense. I'm going to just write it like this formally. And you expand the theory in terms of the following variables. So capital Q is e to the 2 pi I n over k plus n. And GS is 2 pi over k plus n. And this is supposed to give you the topological partition function of Y. So let's say the Gromov-Witten theory of Y in terms of the variables GS and Q. So basically what this is just a generating function for Gromov-Witten numbers. You sum over all possible. So you have a degree which counts how many times you wrap P1, right? You have a degree there, and then you have a genus, which counts the genus of the curve, and then you have some Gromov-Witten numbers, and you're summing them, and you put Q to the D, and then GS. This is okay. Well, GS, I hope it's not going to be too confused to 2G minus 2. Okay, so now this is what, as I said, was proven by Gopal Kumar and Vafa by explicit computations. Okay, and eventually this was developed into, topological vertex and so on. But now, what Oguri and Vafa did a few months later was to add knots to the picture. So basically, they added knots by putting in more Lagrangian cycles. I keep forgetting where this thing is. Okay, so if you put more Lagrangian cycles, so what you do, you add non-compact Lagrangian cycles to both sides of the duality. Okay, so you're supposed to. So now on the deformation side, what they did was to add. We put an, let me call it L. You have a Lagrangian cycle here. It's topologically, this guy looks like just like topologically it's a cylinder. It's R2 cross S1, and it's constructed. Basically, it's basically the picture you get. So this is the zero section, the sphere sitting inside as a zero section. L, in fact, you take an unknot in here, an unknotted circle, and L is just the total space of the dual, dual of the normal bundle of this. Let me call it K. K inside S3. So this gives you some Lagrangian cycle, which is linear along the fibers. So it looks something like this. Okay. And now what Oguri and Vafa showed was that if you because we have the intersecting branes in this configuration, because remember we had an n branes here, and you put some arbitrary number of m branes here. All of them a branes, of course. We're doing. We have intersecting branes, so you're going to have x squared zero modes because of strings stretching between these two Lagrangian cycles. And if you integrate them out, you're going to get this so-called Oguri-Vafa operator, which looks like this. It's a sum over n greater or equal to 1, 1 over n. You have it's a trace operator, so it's a trace of, I'm going to explain what this is. Let me just write it first. U is the holonomy, U is the holonomy of the Chern-Simons connection, the connection A on K, so A being the connection that lives on this brane. And then you're going to take some background flat connection on the non-compact guy, and you say that V is the holonomy of some background, let me call it B. This is a background flat connection on L. And that's the way you couple the two cycles. And now what you're supposed to do is to take expectation values of this guy in Chern-Simons theory, and you're going to get knot invariants, and in fact you get all colored knot invariants, so colored by any representation of UN. But for now in this talk I'm only going to talk about the simplest possible case, namely the fundamental representation, which corresponds to taking n equals 1 in this formula. So I'm just going to I'm going to ignore the high order pieces. You can do that. You can study the duality term by term, order by order. So for n equals 1, you just get trace U trace V, and if you take the expectation value, as I said, you just get a knot invariant. So the knot invariant you get, it's just the Humphrey invariant of the unknot. So then the duality says the following: log n. Before I can say log n, I have to tell you what happens through the transition. So now remember there is an extremal transition here, topology change transition. So you have to understand what happens to L through the transition. So this is a key point in formulating this duality for knots. So you have a picture like this. I mean, you start with some cylinder here, and you try to understand what it goes to on the other side. Well, what you're supposed to do is to take this limit in which mu goes to 0. And then what happens? Well, you get a singular cone here, and the Lagrangian itself is a cone inside here. So there is some L0 which is singular. It's a cone, because this circle gets squeezed to nothing, to a point. So you get some cone inside, so it's a singular Lagrangian, and then you're supposed to somehow blow it up. You have to do probably a symplectic blow up to understand what really happens to the Lagrangian. And the picture here is once you got a P1, the Lagrangian in this particular case turns out to be, at least if you make a good choice for the knot K, it turns out to be again, it's a Lagrangian cycle I'm going to call M in here, which again, it's R2 cross S1, and it intersects P1 along the equator. So this is just the equator of P1. All right, so now you can say what happened, what Lagrangian duality is in terms of formulas. I'm going to leave that there. So let me just. So in terms of formulas, what you learn is the following. You learn that if you take the Lagrangian limit of the Humphrey polynomial of the unknot, it's supposed to match some Gromov-Witten generating function on the blow-up as follows. So if we take, again, log n, limit at n goes to infinity of the Humphrey polynomial of the unknot, okay, which is, well, it's really a rational function. It's a function of, again, n and the level k, and you're supposed to use the same change of variables. So you have to, again, choose the same, you keep fixed q and gs the same way. I'm not going to rewrite that. This is supposed to match some Gromov-Witten series of y with boundary conditions along M, which is now, it's a function of q and, gs and q. And here, this is not a full generating series for this situation over there. It's truncated to h1, so let me write here h equals 1, so this means that the source has only one boundary component. So this is what the source looks like when you do Gromov-Witten stable maps. The domain of the stable map has only one boundary component, and I'm going to insist on this boundary component being mapped to the equator with winding number 1. So I also truncate to w equals 1. So it's going to be mapped. So if you map this to the equator, just the boundary component is mapped to the equator, and it's mapped with winding number 1. And this truncation corresponds, I mean, it reflects the fact that here I truncated to n equals 1. And I went throw away the others because I'm just interested in the Lagrangian dual of the Humphrey polynomial, not the colored Humphrey polynomial. For now. I mean, certainly it's very interesting to look at the colored invariants, but for now I'm not going to do that. I mean, in this lecture I'm not going to do that. Okay, so then the statement, so this is the statement again. Well, okay, this is it's a what Oguri and Vafa predicted, and it was checked by explicit Gromov-Witten computations. So checked by explicit computations, explicit localization computations by Katz and Liu, Sheldon Katz and Melissa Liu, who actually did the Gromov-Witten computation here. Well, modulo some technicalities that I think they're not even sorted out up to today. But anyway, so you can do a localization computation in this theory and actually check that this works. K is just the unknot, yes. Just the unknot for now. I mean, I'm gonna the whole point of this is to try to do more than that. But for now, this is just the review. Okay, and now I should say there is an important observation here, which tells you that there is another way of thinking about these invariants if you embed the story in string theory, as opposed to doing just topological models on some targets, on symplectic target spaces. We can try to you can think about what happens if you embed it in string theory, and this also goes back to Oguri and Vafa, and also related work by Labastida, Marino, and Vafa. So in M theory, what happens? In M theory, what happens is that you want to look at Y at the resolved conifold, and I want to discuss there is a P1 in here, and there is this Lagrangian M that intersects P1 along the equator. And we want to place some M5. Well, you can even do for this particular case, because I don't have colored invariants, I can only get away with one M5 brane. So I have one M5 brane on M. Okay, but now what's cool about this problem is that you have this holomorphic disk, right? Because you have the P1 in here. So if the Lagrangian M intersects here, and you have holomorphic disks ending on the Lagrangian, obviously. So you can ask the question of, so if you have holomorphic disks, then you can wrap, you have supersymmetric M2 configurations wrapping the disks. So I have a disk here D plus and another one here D minus. So I have M2s. Okay, I put one, you can look at M2 configuration, open M2s wrapping the disks D plus and D minus. So now you can ask, well, can we compute the degeneracies of such objects? They are supersymmetric membranes. If you look at the 5-dimensional effective theory, they're going to look at BPS, massive BPS particles. So you are supposed, so they're going to have some degeneracies, right? So you get, from here you get some BPS particles in 5D, and you can ask about degeneracies. How many? 5, 7. Well, and the nice thing that Oguri and Vafa showed by physical arguments showed that, in fact, what happens is that the degeneracies are determined by the Humphrey polynomial of the unknot on the other side of the duality. So if you embed the story in string theory, the Humphrey polynomial determines the degeneracies. And it's actually, in this case, it's very simple, so we can do it right now. Just to give you an idea of how this works. So if you look at the Humphrey, with a certain normalization, of course. So if I took the Humphrey of the unknot, it's going to look like this in Lagrangian variables. It looks like this. And the important observation is, let me write this as plus minus 1 times that. And there is a 1 here. And this is telling you, this number here is telling you that there is exactly one bound state, one open M2 bound state on D plus. This one is one open M2 bound state on D minus. The sign is a little bit subtle, so I'm not going to discuss the sign now. The sign has an interpretation which can be understood, but let's ignore the signs for now. And important is that these numbers, I mean, the arguments of Oguri and Vafa tell you that there are no more. This is all that you can get. These are all the possible bound states for this configuration. So we can read off the bound states by just looking at the Humphrey polynomial. That's the upshot of this. Okay, so that's going to be important for us. So this is sort of the situation that was the way it was 10 years ago. And since then, well, we learned many things, the topological vertex and so on, but the problem is it was very hard to make progress in this, because it's very hard to, to understand what happens if you pick up a knot, pick up the Lagrangian, go through the transition, and try to understand what happens in the resulting Gromov-Witten theory with Lagrangian boundary conditions. It seems to be a very difficult problem. Okay, so now what happened recently is that further progress was just kind of was very strongly encouraged by this conjecture of Blomkov and Shende. So let me just try to summarize that in physics terms. It's not going to be so they formulated a conjecture in pure mathematical terms, and I'm not going to go through that in mathematical terms, but let me summarize what the conjecture says in physical terms. So suppose you take now, so this conjecture, I should say, it's for now is not the way it was formulated. It was not formulated in terms of a Calabi-Yau threefold or anything like that. So a priori, it was not very clear how to embed that in physics, and actually this was one of the goals of this work with Vivek and Kumgun, to understand how that is embedded in a string theory situation. So you take a plane curve. It's a plane curve in C2 determined by a polynomial equation f of x, y is 0. And suppose it has one singular point at the origin at some singularity, whatever it is, and there are no other singular points for simplicity. I don't gain much by allowing more. And what's being done, for many years, it has been known, of course, that if you take this curve and you intersect it with the spheres of radius epsilon, but small epsilon, centered at the origin, so positive but very small epsilon, what you get is, of course, it's a one-dimensional thing that this is the so-called link of the singularity. So it could be a link, or in some cases it's a knot, depending on the structure of the singularity at the origin. So this is what's called in knot theory, it's an algebraic link or knot, depending on the situation. So it comes from, it's not just a random knot, it just comes from, it comes from curved singularities. And I should say these are not a majority in the space of all knots. This actually is a minority. There are many more knots than algebraic knots, and so for that reason, it's certainly a step forward, but it doesn't solve the problem completely. Okay, so for example, if a few examples which are actually the best understood from many points of view are the following. You can, for example, take, well, okay, so let me just discuss a few examples. Suppose f of x and y is just x, so there is no singularity, it's just a line passing through the origin. Then the knot is unknot. Then the link you get is the unknot. There is no linking. There is no nothing. Now suppose f and x and y is x times y. So now what you get, it's a cross of two complex lines, the coordinate axes in C2, which intersect. So this is just an ordinary double pole, double point. So this is going to give you the Hopf link, which is just two knotted circles with certain orientations that I'm not going to try to get right now. And then another one, more interesting perhaps, if you suppose it's x cubed minus y squared. Well, then you get something called a trefoil knot, and I'm not going to try to draw it because I'm going to end up embarrassing myself. So it's just a trefoil knot, and as I said, I'm not going to try to draw it on the blackboard, but it's some connected knot. And you can do more things. You can do x, y equals x to the p minus y to the q. And if p and q are co-prime numbers, you get the so-called torus knots. If you If they are not co-prime numbers, then you get links. So they are certainly more complicated things. So this was just for P and Q co-prime. Okay, so that's some story that was known for a very long time, and you know, it's these links, the algebraic links are very well classified in terms of the singularity types and so on and so forth. So there's been a lot of work done on this subject, but kind of not very recent, because this is kind of an old story.
Those are only torus links, probably.
Which ones?
PQ not being co-prime will give you torus links.
Probably, yeah. You get them linked somewhere, yes. Okay. So anyway, yeah. All right. So what the blocker exchange? I mean, well, let's just say there is previous work, not so recent, by Gusseinzadeh and sorry, I can't remember the other name. But the structure is the following. So I'm going to say it in pure physics terms. So what this OS conjecture says is that take a gas. Imagine you have a D2 brane. This is formal because, as I said, this is not embedded in string theory for now. So I'm just translating what they said in physics language. So it looks something like this. Imagine you have a D2 brane on C. One D2 brane on C. And you put a gas of n D0 branes inside in the D2. And you want to study this partition function, the partition function of this gas. Let me see where. Okay, anyway. So you can construct a partition function. For lack of a better name, I'm just calling it OS, which is a function of some chemical potentials. So we're going to have one Q. Of course, you have to have two of them. Let me write it like this: a small q and a capital Q. So it's sum of some degeneracies. There is an m and an n, and you have some degeneracies mn, q to the n, capital Q to the m. So I should tell you, n obviously is just the number of the zero branes, so there is no mystery there. But I have to tell you what m is. And m, for now, I'm just going to skip the mathematical definition of m. M is some kind of multiplicity. Some kind of multiplicity at the singular point. That, well, it has a very precise mathematical definition. I'm just suppressing it. Maybe I should just say it in words in case somebody would rather hear the mathematical definition. Is that what these things are? You have to think of them as ideal sheaves of points on the curve, and m ends up being just the minimal number of generators of the ideal sheaf at the singular point. So there is something singular. There is something rigorous behind it, but I'm suppressing it. So there is some gas like this. There is some partition function like this that can be computed. In some cases, it can be computed for torus knots by fixed point theorems. And what they conjectured is that this partition function actually computes the Humphrey polynomial of the link, up to some prefactors that I'm not going to try to get right. But some kind of very simple prefactors, depending on the Milnor number of the singularity and so on. You have the conjecture says that ZOS of these two variables equals the Humphrey. I'm going to just put some. There's some prefactors that are not difficult. Times Humphrey of the link or the knot, whatever you have there. And it was proven for torus knots, because it turns out you can use a localization computation to evaluate this, and you can check it. You can prove this. So this was proven by OS. Okay, and it's conjectured to hold for any such a knot or link, but it seems that there isn't a very good idea around how to prove this in general. Well, it's a degeneracy. It's something that I'm suppressing. It's whatever it is. It's the degeneracy of this. It's a number of microstates of this gas with certain keep, well, with n the zero branes, and then you have to, as I said, there is some multiplicity thing that you have to specify at the singular point that I'm suppressing. I can tell you more precisely what it is if you rather hear the mathematical definition. There is it's the Euler character of some stratum in the Hilbert scheme of points in the end. I mean, there is a topological definition for this. Okay, so that's the story that Oblomkov and Schende told. And as I said, a big motivation for our project was to try to understand how does this fit in string theory, and is this related to Lagrangian duality or not? And it turns out that it is, and there is an interesting construction behind everything here. And it goes as follows. The key point, as I said, is to try to, well, I mean, when you do this Lagrangian, the way I did Lagrangian duality for the unknown, as I remember, I erased it now, but we had to go through this singular Lagrangian Lagrangian cycle. So the first idea, so we want to embed in string theory, so in string / Lagrangian duality. So how it goes? Well, one thing that you have to realize is that there is another way of placing these Lagrangian cycles in these transitions. So you can, instead of taking, as we did before, a picture like this, in which the Lagrangian cycle goes through the sphere, and then if you contract the sphere, if you specialize to the singular point, you get some kind of a singular Lagrangian cone. You can do something else. And this was observed again in some older papers of Kumgun and collaborators. We kind of reloaded it and understood it better. So what you can do is try to, before going through all this process, try to move this Lagrangian cycle off the zero section in such a way that it doesn't intersect the zero section anymore. So this is something we call a lift. So and the reason for doing that is because we want to have a transition in which the Lagrangian cycle is smooth at every intermediate point, including when the conifold is actually singular. Okay, so in some sense, if you like symplectic geometry, what's going to happen is that we want to get the Lagrangian cycle on the blow-up from this one by some kind of symplectic surgery. This is what's really going on. And in order to do that, it's much better to avoid going through the singular point. So you have to lift it first. Now, of course, if you immediately you can, there is an immediate objection to this, which says, well, if you lift it, how is it going to talk to the sphere? Because they are disjoint, so there is all the open strings are massive. So how are we going to get any kind of effective interaction terms? And this is something that was pointed out by Witten in '91. So you have a lift. Okay, so I should have erased this, but okay. So you have a lift of the Lagrangian cycle. So let me draw the picture on the deformation side. S3. So it's lifted, which means that it's somewhere here inside the total space of the cotangent bundle, but it doesn't intersect the sphere anymore, the zero section. And the way they talk was pointed out, as I said, by Witten in '91, is that it depends on how you do the lift. But if you do it in a careful way, you can make sure that there is, in fact, an open string instant on top which couples them. So you have a holomorphic cylinder which couples the two theories. And actually, if the construction is right, it turns out it's a unique holomorphic cylinder, which is highly non-trivial. I mean, this is a very important condition. In other words, you have to make sure you don't get families of these things. If you get families, you have problem of zero modes. It's not clear what they contribute. I mean, what kind of effective couplings you get. So it's much better to get at least, if not unique, at least rigid holomorphic disks. But in this particular case, for the unknown, you can actually show it's unique. Okay, so now they couple like this, and now the operator. So now you get some open string corrections, and it's very simple to. It's a really simple computation to sum them up. So you're really doing some multi-cover computation in the Gromov-Witten theory with the Lagrangian boundary conditions on these two cycles. So you get something like this, which looks precisely as an Oguri-Vafa operator, but to get these terms weighted by an instanton, the instanton action, right? In the integral of the symplectic form on C, you get that n times, because, so sorry for the confusion. Let me call this maybe A. This is not a curve, this is just an annulus. N over n, and then a couple trace of u to the n, trace of v to the n, just like before. So apart from these instanton factors here, you get the same operator, and these guys can be absorbed in the definition of v, and you can forget about them. They don't play any significant role. Okay, so in other words, you just replace this intersecting Lagrangian cycles by two Lagrangian cycles just disjoint, but they somehow are coupled via this open string instanton effect. And what happens on the blow-up? Well, what happens on the blow-up is very similar. You move the Lagrangian cycle I called M in such a way that it no longer intersects the P1, the curve of the compact curve of the conifold. So on the blow-up side, you get a picture like this. This is P1. The Lagrangian cycle used to be here somewhere and cut along the equator. Well, now it's no longer there. It's somewhere inside here. It no longer cuts along the. There is no common point between these two guys. But what happens is that you have a holomorphic disk, which intersects P1. So now I have a holomorphic disk in there. So I call it D. Okay. So now you have this structure. So now you moved it. Before we had a cut here, so we had two disks. Now we have only one. And again, the conjecture is that if you compute the Gromov-Witten theory of this configuration here, it's supposed to match the not invariance of the unknot in this particular case. And now, if you think of, so it's true. Again, you can do the computation as by analogy with this Katz-Liu computation, and it's true. So log_gen is still log_gen holds again. But what's interesting, if you think in terms of BPS numbers in M theory, what you do, remember the Humphrey of the unknot was something like 1 times q to the 1/2 minus 1 times q to the minus 1/2 divided by q to the 1/2 minus q to the minus 1/2. Now you have to identify these coefficients. Their geometric interpretation is different. So this one counts the BPS bound states, so open M2 bound states, wrapping the disk D. And this one used to count the other disk, but there is no other disk. This one counts the same thing, open M2 bound states, wrapping the union of D with P1. So these are objects that are made of two branches, if you want, two components, and the way they manage to bind to each other is because they intersect. So whereas this is a bit harder to understand in M theory, in M2s, but if you take a type 2A limit and you study the open string stretching between these guys, if you make them D2 branes, you can understand that they form bound states. And so this is how you have to think of these coefficients of the Humphrey polynomial in terms of bound states of this form. And actually, this is a much better point of view for geometric reasons. And this is the picture that actually generalizes easily to all algebraic knots. And I'm going to explain how that goes. And the observation is actually very simple. The main idea is very simple, but having it carried out in practice involves all sorts of technical details of how to construct Lagrangian cycles, how to do Lagrangian surgery, and so on. I'm going to skip all that. But I should say it's fairly hard work to actually make the picture, this idea actually, to implement it concretely. What happens is the following. Now, remember in the OS picture, we started out with some curve in C2, well, which was singular at the origin, right? Well, it's a very simple thing. So now I'm going to start on the blow-up side. It's easier to say what happens on the blow-up side. Well, there's a very simple way of embedding such a curve in the conifold, in the resolved conifold, because the resolved conifold, remember, it's just a rank 2 bundle over P1, right? And you can, all fibers, so basically the fibers here are C2, all complex planes. They are just there. So what you do, let me draw the picture like this. So this is the complex. This is, you pick up any fiber, whichever you want, because I'm not, pick up a specific fiber and put the curve inside it. So I'm going to have a singular curve C in here. Okay? That's a trivial construction. And then take a sphere of radius, let me draw it like this. A small sphere S3 epsilon, the way we had before. They're going to intersect. Well, obviously, it's very hard to draw. So this point is meant to be a whole knot. So you get this algebraic knot or link. Let me call it knot. I'm assuming it's connected. Living here. So now what turns out you can do, and that's the part that's very technical, as I said, but it can be done very explicitly. You can actually construct a non-compact Lagrangian cycle that passes through this knot, that intersects the curve along this particular knot. So you can construct an M inside Y, which is disjoint from P1. There's no intersection. So the conditions are that M intersects P1. Well, the intersection is empty. So it's kind of, okay, so maybe I should draw this picture. Yeah, it's just like this picture, except that this point is going to be singular on D, right? I don't have to draw it again. I just have to make sure that this point looks like a singular point. So now when they intersect, there is a singularity here. And you can construct an M like this, and it passes precisely through this knot. So the intersection of M with the curve C is just the knot. Such a way that you get a well-defined, I mean, up to, again, technical details related to the Fukaya construction, you get some well-defined Gromov-Witten theory with Lagrangian boundary conditions.
Is M Lagrangian cycle?
Yes, it's Lagrangian.
Is it a compact or?
No, it's the same topology. M has the same topology as before. It's just topologically, it's just a cylinder. The hard part is to try to fit it in, to try to make it intersect C the way it's supposed to. So I'm going to suppress how that is done, but it can be done very, I mean, we have very explicit constructions for this. And moreover, you can actually study now, because this is off, doesn't intersect the zero section anymore. You can study, you can understand what happens on the other side. You can complete a whole geometric picture of the transition. And again, on the deformation side, you get exactly what you want to get. Namely, you get something that you have some Lagrangian L not intersecting the 3 sphere, and you can, if, as I said, with enough work, you can prove that there is an annulus here between this. So let me draw this bigger. Okay, so this is some holomorphic cylinder, and which ends up here on S1. But here it ends up on precisely on this whatever torus knot you're supposed to have. So there is, or sorry, algebraic knot you're supposed to have. So there is a holomorphic cylinder here. And for torus knots, you can actually prove this cylinder is the annulus is rigid. For more complicated knots, I don't know. It's only conjectural. We can't prove anything. We can prove that this annulus it's rigid, or it could be. It might as well come in families, but we believe it doesn't, except that we don't know how to prove it. Okay, so you get this picture, and here, as I said, you get the right picture, with the exception, with the difference that here you have a singular point when they meet, and that's very interesting geometry. So I guess I won't really get into the technical details of what you're supposed to do here, but there are two ways of dealing with this. You can try to do the computation in Gromov-Witten theory with Lagrangian boundary conditions, and this is something that can be done in detail. So let me just mention the results now. Where should I put the results? Yeah, okay. So what you can do, again, with enough patience and enough effort, you can do the following. So what you can do, well, first of all, you can do the A model computation. The A model computation on Y with Lagrangian boundary conditions on M, and we only did it for one boundary component, any genus, one boundary component with winding number 1, genus anything. That can be done basically by once you understand understand sufficiently well the formalism of Katz and Liu, you just can generalize it. So you're using ideas, using the idea of KL, Katz and Liu. This can be done by equivariant localization, and you can prove that it agrees with the Humphrey polynomial of the torus knot, and agrees with. Oh, I should say this is only for torus knot. So sorry, I apologize. This is just for computation for PQ torus knot. Because I need to use localization. I need a circle action, which won't happen unless the curve is in this special form. And agrees with Humphrey. Okay, so that's one thing. And the other thing, you can try to think, well, what happens from the M theory point of view? Can we count bound states? Because you see, if you remember when I said Oblomkov and Shende, what they did nothing like Gromov-Witten theory. They numbers, those n of M and N that I wrote down, and I didn't explain how they are mathematically defined, have nothing to do with Gromov-Witten numbers. So the insight is that, in fact, they have to do with BPS numbers. Okay, so you can try to do the M theory computation. So that's the second result. BPS computation. And this is this work, and that's going to appear soon, hopefully, with Zheng Hua and Jan Soiberman. And you can prove it agrees. It agrees both with Oblomkov, Shende, and the Humphrey polynomial. So, and agrees with OS and Humphrey. Well, if it agrees with one, it has to agree with the other, because they already proved that they're the same thing for torus knot. Okay, so you can prove that it's there, that the agreement is obtained. And somehow this computation carries a lot more insight. I mean, it provides a lot more insight into what's going on here. I mean, the Gromov-Witten computation is nice, but somehow it just said, yeah, it works. But this gives you more insight. So in particular, this can be generalized to define motivic knot invariance for algebraic knots. If you use the theory of Kontsevich and Soiberman, using Kontsevich and Soiberman. I mean, basically applying Kontsevich and Soiberman to this particular situation. So it's an application of.
You also have to reduce the torus knot, restrict the torus knot?
No, to define, no. To compute, yes. To define, no. To construct the invariance, no. I mean, to the extent that, well, I mean, there are some conjectures in the theory of Kontsevich and Soiberman. There's some general conjectures that are supposed to work in order for the whole construction to work. But apart from that, no. To define, you can define them. Now, the computation, no. It can only be done for torus knots, and even then, it's complicated. So, yeah, actually, thank you for asking this. For torus knots, we can prove there is actually a new paper of Oblomkov and Shende which appeared today, and we can prove for torus knots that this motivic invariance. So let me remark. I think it's a good time to stop. Actually, let me just last thing I want to say. So there is new results of Oblomkov and Shende with Rasmussen, with Jake Rasmussen, OSR. This stands for. In which they just propose a construction for refined or KR Kovanov-Grozanski invariance. So you get a geometric, if you want, geometric construction of KR invariant. And for torus knots, they proved that it agrees with the homological invariance. And what we can prove is that these motivic invariants actually are in agreement again with the refined thing. So it agrees with motivic, with the motivic construction. And for this, you don't need the explicit compute. I mean, you don't need to compute both sides and check. It just you can prove geometrically that it agrees. Okay, so I think it's a good point to stop. And if we need questions.
Are there any questions?
So is it only for torus knot?
Which statement?
I mean, even in the topological string
If
computation.
you do that, only for torus knots, because I need a circle action. So the only curve that has a circle action is x to the p equals y to the q. If I perturb that, I don't have a circle action, so I can't compute anything.
So this is for home fly polynomials. Can
Yeah.
it go beyond fundamental representation?
Yes, you can go beyond fundamental representations on both sides, but it's hard. I mean, yes, in this story, so let me see. In this story, there is a, yes, in this story, basically going beyond fundamental means allowing all H, all W. It's a very messy computation, but it can be done if you're really determined. And you have 3 months to waste. I mean, well, maybe not waste it, but 3 months to not do anything else. You can probably get it done. Here, there is a natural construction. Again, this can be generalized to colored invariants. But again, doing any computation, it seems to be very hard. I mean, and proving that the disagreement is very hard. It's basically technical. I mean, in both cases, it's technical. It's technical issues that they have to deal with. But conceptually, the construction is generalized. Yeah, both constructions generalize. Yeah, that's. We are trying to find there's got to be some cool set of tricks allowing you to deal with the colored invariants, at least in this particular model. But we're not there yet.
Does that computation by localization with circle action reproduces matrix model by Marcus Marina?
What it reproduces is this S matrix formula.
S matrix model.
So basically, you don't have to do the whole computation and check the numbers. You can prove that the relation between PQ knots and the R knot is the same as the one predicted by the S matrix formula.
Mm-hmm.
So you can just prove the same relation in the topological A model. You don't really have to compute and check that degree. By just comparing the contributions of fixed loci.
Are there any further questions? Shall we thank the speaker again?